Hi y'all. In this video we are going to be going over all of the different types of problems that you see in the roots and powers quiz, simplifying radicals, and working with exponents. Let's start with something simple. We have something just like the square root of 25. That means we want to know what number times itself makes 25. The number that you multiply by itself to get 25 is 5. So the square root of 25 is simply 5. Yes, it's that easy. Square root of 160 is, we need to simplify by breaking that down into something we can take the square root of. We need to find a perfect square that's a factor. There are lots of ways to break down 160. You could do 4 times 40, 2 times 80, but the one that has the biggest perfect square as a factor would be 16 times 10. Take the square root of 16. The square root of 16 is 4. We cannot take the square root of 10 because that's irrational. It would give us a long decimal. So we're going to leave that as the square root of 10. All right, when you add in a variable, you'll need to do the numbers and the variables separately. Let's start with the square root of 32. The square root of 32 has, again, several different possible factors. You could do it as 4 times 8. The problem with 4 times 8 is even if we took the square root of 4, that would still leave an 8 under the radical, and 8 still contains a perfect square, which is 4. You want to find the biggest one possible, and the biggest one possible is 16. The square root of 16 is 4. Now, as far as the square root of x to the 18th, here's what we need to know. We should remember the exponent rules. Of course, somebody's got a ride waiting. It's after school. We know that x to the 9th to the 2nd power is x to the 18th because 9 times 2 is 18. So what we'll need to do then is realize that when you take the square root of x to the 18th, you're undoing the square, and the square root here would be x to the 9th. Take half of the exponent, you're pretty much good to go. Anything that we were able to take a square root of goes in the front. Anything that we were not able to take a square root of because it was irrational is going to stay underneath the radical. All right, same as before, we look at the 18 separately from the variables. The 18 can be broken down as a 9 and a 2. We're looking for a pair of numbers in which one of them is a perfect square. 3 times 6 would not help because 3 is not a square and 6 is not a square. Now on the variables, what we want to do is find things we can take half of. We could take half of 7, but it would be a fraction, so that's not going to work. Instead, we break it down into the biggest thing we can take half of, which would be 6, and 1 extra. 6 and 1 makes 7. The b to the 10th, we will be able to take a square root because we can take half of 10. All right, again, anything we can take a square root of, that's what we're going to do. The square root of 9 is 3. The square root of a to the 6th is a to the 3rd. The square root of b to the 10th is b to the 5th. Let's see what we could take a square root of. We took out the 3, we took out a cubed, we took out b to the 5th. The ones we were not able to take a square root of because they were irrational, we leave as 2 and a under the radical. Now I do need to point out, this is a minor thing, but I am going to go ahead and clarify that in this case we are making the assumption that every single variable here represents a non-negative number. When the variables have the option of representing negatives, it gets more complicated. We will leave that for a later course. Okay, super simple. Square root of 5 times square root of 2, square root of 10. If you don't believe me, check it out on a calculator. Okay, sometimes you have both numbers and power and radicals. You're going to multiply the numbers. 4 times 5 is 20. You're going to multiply what's under the radical. 2 times 7 is 14. And that's it. You always do want to check and see if there is now maybe a square under the radical. There is not, so we leave it as it is. There are multiple ways to approach this one. One option would be to start breaking down the 15 and the 35 ahead of time. Another option is just to multiply them. If I just multiply the 15 times the 35, I'm going to get square root of 525. And 525 can be again broken down into a 25 and a 21. And we could work it this way. The square root of 25 will be 5. It might be easier, however, if you took the 15 and the 35 and you broke them down ahead of time. The square root of 15 is 5. Sorry, no it's not. My mistake. The square root of 15 is square root of 5 times square root of 3. There's also the x cubed. 35 can be broken down as a 5 and a 7 and the x to the 11th. All right, the square root of 5 times the square root of 5 is 5. Let's see, what else do we have? We have an x cubed and an x to the 11th. If we multiply those two together, we're going to have x to the 14th. The square root of x to the 14th is x to the 7th. The ones we were not able to take a square root of was the 3 and the 7. 3 times 7 is 21. If we had approached it by just going ahead and multiplying them first, this is where the 21 shows up, and this is where the 5 shows up. Anytime you want to add up radicals, what you're looking for is like terms. Just as if we had had 8x plus 2y minus 3x, we're going to put together the ones that match. 8 minus 3 is 5. The 2 radical 7 does not have anything that it is going to combine with because there are no other like terms. Sometimes there are like terms, but we don't necessarily see them to begin with. Like the 45 and the 20 do not appear to match. However, we can break down the 45 as a 9 and a 5. We can break down the 20 as a 4 and a 5. The reason I chose a 4 and a 5 instead of, for example, maybe a 2 and a 10 is because 4 is a square. If I did 2 times 10, it would not help me because 2 is not a square and 10 is not a square. All right, the square root of 9 is 3. The square root of 4 is 2. 3 times 3 is 9, radical 5. 4 times 2 is 8, radical 5. At this point, we do have like terms. The square root of 5 and the square root of 5 are essentially like terms. 9 plus 8 is 17, and we keep the square root of 5. Sometimes people wonder, well, why don't I add the 5 plus 5 to get 10? It's for the same reason that if you have 9x plus 8x, you have 17x. The x portion doesn't change. If you have 9 cats plus 8 cats, you have 17 cats. You do not have 17 double cats. You just have 17 cats. Alrighty. When you are looking at a fraction, you should know that we need to rationalize the denominator. However, in this case, it's not going to be a necessary step because the fraction can simplify before we ever get to the rationalized step. The square root of 20 can be broken down as a 2 and 10. Now, why on earth would I break it down as a 2 and a 10 when 2 and 10 are not squares? I've chosen to break it down this way because I saw that in the denominator there was already a radical 2. The radical 2 cancels the radical 2, leaving us with nothing but square root of 10. Nothing to simplify, nothing to rationalize. We could have simplified the square root of 20 first, but it actually would have ended up making things a little more complicated. Now on the next one we need to rationalize the denominator. On the quiz I observed that quite a few people just did square root 12, or the equivalent with whatever your numbers were. However, this 12 should be simplified first if we want to keep our numbers small. The square root of 12 breaks down into the square root of 4 times the square root of 3. The square root of 2, the square root of 4 is 2, so I have 2 radical 3 for my denominator. We cannot leave a square root in the denominator, so we multiply the top and the bottom by whatever radical we're trying to get rid of. On the top we now have square root of 39 because 13 times 3 is 39. On the bottom we have a 2 times the square root of 3 times the square root of 3 is 3. 2 times 3 is 6. And while it looks like the 39 and the 6 should reduce, they do not, because the 39 is under the radical and the 6 is not. We do want to check and see if there's anything that can simplify, but 39 does not have any perfect square factors, so we're done. All right, same thing on this one. We could just do square root 90, but that's going to give us some really big numbers. This will be easier to work if we break it down first as the square root of 9 times the square root of 10. Why 9 and 10 instead of 2 and 45 or 3 and 30? Because we can take the square root of 9. The square root of 9 is 3. We have 3 radical 10 for our denominator. Again, we're trying to rationalize the denominator. So to get rid of anything that's in the denominator that is a square root, we multiply by that same square root again. On the top, we now have a 3, and we have a square root of 70. On the bottom, we have a 3 and a 10. Almost done. Unfortunately, we do have one more step yet to go. After simplifying, we ended up with a whole number on the top and on the bottom with a common factor. We can divide this by 3, we can divide this by 3, and when we're finished, we have a radical 70 on the top and a plain 10 on the bottom. Again, it looks as if that should reduce. It does not. The 10 here is under the radical, the 10 here is not under the radical. So the matching factors of 10 are not really matching factors of 10 at all. All right, we are finished at this point with the radicals. Now moving into the exponents. The quotient of powers rules tell us that when we have x to the a over x to the b, we have x to the a minus b. So the rule here is that we should subtract the powers. 8 minus 4 is 4. If you picture this written out, this would be 8 x's all in a row being multiplied. This is 4 x's in a row being multiplied. You'd be able to cross off 4 of them, leaving 4 still not canceled out. X to the third times x to the seventh. The rule here is x to the a times x to the b equals x to the a plus b. We need to add the powers. 3 plus 7 is 10. If you think about that one written out, we would have x times x times x times x times x, 7 more. Total of 10 of them in a row, x to the 10th. When you have a power outside of parentheses, that power is going to apply to each of the factors in the parentheses. The 4 in the x is not a single unit. This is a common mistake to think that the 4x is somehow like connected. This is a 4 to the third power. This is an x to the third power. This is a 5 to the third power. So we would need 4 to the third, x to the third, and 5 to the third. When we're done, the 4 cubed ends up being 64. The x cubed is just that. And the 5 cubed, 5 times 5 times 5, is 125. Negative exponents do not make the number negative. We do not get a negative value. Instead, what that negative exponent does is it basically takes a reciprocal. So we take whatever the positive version was, which would be 7 squared, and we make it the denominator of a fraction. 7 squared is 49, and there we go. All right, what have we got? We have stuff. We have 0 power. We are done. Next. 1/2 power basically means square root. So when we take something to the 1/2 power, that means we need the square root of the number. The square root of 64 is 8. If it's easier to think of as breaking this down maybe into the factors, you could think of 64 as being 8 times 8, and we need half of those factors. Half of the factors would be 8. X to the 2/7. This means we would need to take x and break it into 7 equal factors. This would be the 7th root of x. The 2, the numerator, tells me how many, and that means I would need 2 of them. So the way that we record this is we say we are going to take the 7th root of x, and then we need 2 of them. It's not as easy to see with a variable, it's easier to see with a number. 81 to the 3/4 power is the exact same thing. That means I need to take 81 and break it into 4 equal parts. So in other words, I need to take the 4th root of 81. Then I will need to take 3 of them, so that will be to the 3rd power. The 4th root of 81 is 3. To the 3rd power gives me 27. Might be easier to think of in picture form. So if you think of 81 as being broken into equal factors, 81 is equal to 3 times 3 times 3 times 3. 3 times 3 is 9, times 3 is 27, times 3 is 81. These are all of the factors of 81. However, I want the fraction 3/4 of them. So breaking it into 4 equal parts and taking 3 of them, I would have 3 times 3 times 3. 3 times 3 is 9, times 3 is again 27.